How can we turn solar energy into plasma to power everything? You can use solar energy to create and control plasma, but plasma isn't a magic fuel. It's an energy state in a medium. The real trick is using plasma as an intermediate layer to convert, store, transmit, or transform solar energy more efficiently than conventional electricity. Here's the clear, physics-grounded picture. What plasma actually is. Important reset. Plasma is ionized matter, gas so energized that electrons are stripped from atoms. Examples: lightning, auroras, the sun itself, fusion reactors. Key point: plasma does not generate energy on its own. It consumes energy to exist unless nuclear fusion is occurring. So the real question becomes, how can solar energy be converted into plasma and then used productively to power civilization? Turning solar energy into plasma, the core pathways. Concentrated solar to thermal plasma. This is the most realistic near-term method. How it works: vast mirrors or lenses, heliostats, Fresnel lenses concentrate sunlight. Temperatures exceed 3,000 to 10,000 K. Gases, air, argon, hydrogen, CO2 ionize into plasma. Plasma becomes a high-energy working fluid. What this enables: plasma turbines, no solid blades to melt, ultra-high temperature chemical reactions, waste destruction and material synthesis, hydrogen and synthetic fuel production. Already real solar furnaces, France, Spain, plasma gasification reactors, high-temperature solar chemistry labs. This is solar plasma work, not solar electricity plasma. Solar electricity to electromagnetic plasma confinement. Here solar panels generate electricity, which then sustains plasma. Process: solar PV electricity powers, arc discharges, RF plasma, microwave plasma magnetic fields shape and stabilize the plasma. Used today in semiconductor manufacturing, plasma propulsion, materials processing, experimental energy storage systems. This is flexible but less efficient due to conversion losses. Direct solar ionization, advanced experimental, the most futuristic path. Concept: high-energy photons ionize gas directly, occurs naturally in upper atmosphere. Solar corona, space plasmas, possible future tech. Photon ionization reactors, solar pump plasma chambers, space-based plasma collectors. This requires very intense sunlight or space environments. How plasma can actually power everything. Plasma is best used as a universal energy interface, not the final output. Plasma to electricity, next-gen power plants. Plasma enables solid-free power conversion, magnetohydrodynamic, MHD generators. Plasma flows through magnetic fields. Electricity extracted directly. No turbines, much higher temperature limits. This could push efficiencies far beyond steam turbines. Plasma to fuels, energy storage for everything. This is where plasma really shines. Using solar-generated plasma to drive reactions, CO2 plus H2O synthetic hydrocarbons, nitrogen fixation fertilizers, hydrogen production without catalysts, ammonia fuel synthesis. Result: solar energy stored as dense, transportable chemical fuels. This powers aircraft, ships, industry, backup grids. Plasma to materials, infrastructure and tech. Plasma enables solar-powered manufacturing, smelting metals without fossil fuels, producing ceramics and composites, recycling waste into raw atoms, creating ultra-pure materials. Think solar-powered, plasma-based industrial civilization. Plasma to propulsion, transport in space. Plasma is already elite here. Plasma thrusters, ion engines, solar electric propulsion, beamed energy plasma cells. Theoretical, solar plasma motion, without combustion. Could plasma become the primary power medium? On Earth, plasma will be a backbone for industry, fuels, and grid stabilization, not your wall outlet. In space, plasma becomes dominant. Vacuum favors plasma. Solar energy is abundant. No atmosphere limits. Fusion plus solar plasma hybrids become viable. The Holy Grail, solar-driven fusion plasma. This is speculative but aligned with your regenerative planet vision. Idea: solar energy bootstraps plasma. Plasma enables controlled fusion. Fusion releases orders of magnitude more energy. Reality check: fusion requires extreme confinement. Solar alone can't sustain fusion yet, but solar-assisted fusion startups are being explored. Why plasma fits your rainforest-level civilization vision. Plasma systems eliminate combustion pollution, enable closed-loop material cycles, break waste into atoms, mimic stellar processes, like the sun. In essence, solar into plasma, then chemistry and biology to civilization. This mirrors how stars seed planets and ecosystems. You don't power everything with plasma. You power everything by using plasma as a solar-driven transformer that handles extreme energy, enables impossible chemistry, produces clean fuels, electricity, and materials, scales from Earth to space. I will now explain each major solar to plasma pathway and its uses in a rigorous, step-by-step, complete sentence, physics-accurate way, without shortcuts, metaphors, or hype. This will read more like a technical primer than a casual overview. Fundamental principle: how solar energy becomes plasma. Solar energy arrives at Earth in the form of electromagnetic radiation, primarily as visible light, infrared radiation, and a smaller fraction of ultraviolet radiation. When this radiation is absorbed by matter, its energy is transferred to electrons and atomic nuclei, increasing their kinetic energy. Plasma forms when matter receives enough energy that electrons are no longer bound to atomic nuclei. This ionization occurs when thermal energy, electromagnetic fields, or photon energy exceed the ionization energy of the atoms or molecules present. Therefore, converting solar energy into plasma requires concentrating or transforming solar radiation so that it delivers energy densities high enough to ionize a gas. Plasma is not a fuel but a high-energy state of matter that can efficiently transport energy, interact with electromagnetic fields, and drive chemical and electrical processes that are not possible at lower temperatures. Concentrated solar thermal plasma systems. How concentrated solar energy creates plasma. In concentrated solar thermal systems, large arrays of mirrors or lenses collect sunlight over a wide area and focus it onto a small target region. This concentration increases the energy density of the sunlight by several orders of magnitude. When the concentrated sunlight strikes a receiver containing a gas, the temperature of that gas increases rapidly. At sufficiently high temperatures, typically above several thousand Kelvin, the thermal energy of gas particles becomes large enough to ionize atoms through collisions. Electrons are stripped from atoms, and the gas transitions into a partially or fully ionized plasma. The plasma can be sustained as long as solar energy continues to supply heat faster than the plasma loses energy through radiation, conduction, and expansion. How solar thermal plasma is used to generate electricity. Once plasma is formed, it can be directed through channels surrounded by strong magnetic fields. Because plasma contains free charged particles, its motion through a magnetic field induces an electric current through the principle of electromagnetic induction. In a magnetohydrodynamic generator, the kinetic energy of the hot plasma is directly converted into electrical energy without the need for mechanical turbines. This allows operation at much higher temperatures than conventional power plants, increasing theoretical efficiency and reducing mechanical wear. The generated electricity can then be transmitted, stored, or used directly by industrial systems. How solar thermal plasma drives industrial chemistry. Solar-generated plasma provides extreme temperatures that can break very strong chemical bonds. Molecules such as carbon dioxide, water, nitrogen, and methane can be dissociated into reactive atoms and radicals within the plasma. As the plasma cools in a controlled environment, these atoms recombine into desired products such as hydrogen, synthetic fuels, ammonia, or industrial feedstocks. Because the energy input comes from sunlight rather than fossil fuels, the resulting chemical products are effectively solar-stored energy. This process allows solar energy to be converted into transportable and storable chemical fuels that can power sectors of society that are difficult to electrify. Solar electricity-driven plasma systems. How solar panels power plasma generation. Photovoltaic cells convert sunlight into electricity by exciting electrons in a semiconductor material. This electrical energy can be used to create strong electric fields or electromagnetic waves that ionize gases. When a high voltage is applied across a gas, electrons accelerate and collide with neutral atoms, knocking additional electrons free. This avalanche process creates an electrically conductive plasma. Alternatively, radio frequency or microwave energy can be used to excite electrons and sustain plasma without direct electrodes. These plasma systems can be precisely controlled, turned on and off instantly, and operated at a wide range of pressures and temperatures. How an electrically sustained plasma generates useful energy outputs. Electrically generated plasma can transfer energy in several forms. It can emit intense light, drive charged particle flows, or produce high-energy chemical species. The plasma's interaction with magnetic fields allows it to be shaped, confined, and directed with great precision. In power systems, plasma can act as an energy buffer, smoothing fluctuations in solar generation by rapidly absorbing or releasing energy. In propulsion systems, plasma accelerates ions to high velocities, producing thrust with extremely high efficiency. Plasma-based energy storage and fuel production. How plasma converts solar energy into fuels. Plasma provides a reaction environment where temperature and energy are high enough to overcome kinetic barriers that limit conventional chemical processes. For example, carbon dioxide and water molecules can be split into carbon monoxide, hydrogen, and oxygen inside a plasma reactor. These products can then be recombined into hydrocarbons, alcohols, or synthetic fuels using controlled cooling and catalytic steps. The chemical bonds formed in these fuels store the original solar energy in a stable, dense form. This approach allows solar energy to be stored for long periods and transported across the globe using existing fuel infrastructure. Why plasma improves efficiency and flexibility. Plasma reactions are not limited by slow catalyst kinetics or narrow temperature ranges. They can be tuned by adjusting electric fields, magnetic fields, and gas composition. This allows a single plasma system to produce many different outputs depending on societal needs. Because plasma reactors can be compact and modular, they can be deployed at many scales, from small local facilities to massive industrial plants. Plasma-based materials production. How plasma enables solar-powered manufacturing. Plasma provides temperatures high enough to melt, vaporize, or atomize almost any material. Metals, ceramics, and minerals can be processed without combustion by using solar-generated plasma as the heat source. Waste materials can be broken down into elemental components, which can then be recombined into new products. This enables a circular industrial economy in which materials are continually recycled at the atomic level. Plasma processing also allows the creation of ultra-pure materials, because contaminants can be separated or destroyed at high temperatures. Plasma propulsion powered by solar energy. How solar energy drives plasma thrusters. Solar panels generate electricity that powers plasma thrusters by ionizing a propellant gas. Electric and magnetic fields then accelerate the ions to extremely high velocities. The momentum of the accelerated ions produces thrust according to Newton's third law. Because the exhaust velocity is very high, plasma propulsion systems use far less propellant than chemical rockets. This makes solar-powered plasma propulsion ideal for satellites, deep space missions, and long-duration space infrastructure. Direct solar-driven ionization in space plasma systems. How sunlight directly creates plasma in space. In space, solar ultraviolet and X-ray radiation can directly ionize gases without intermediate conversion to electricity or heat. This process naturally creates plasmas in planetary ionospheres in the solar wind. Future technologies may harness this direct ionization by using solar concentrators and magnetic fields to capture and control naturally occurring plasma streams. These plasmas could potentially be used for power generation, propulsion, or radiation shielding. Solar-assisted fusion plasma. How solar energy could assist fusion systems. Fusion requires plasma at extremely high temperatures and pressures so that atomic nuclei can overcome electrostatic repulsion and fuse. Solar energy alone cannot currently sustain fusion, but it can reduce the external energy required to initiate and stabilize fusion plasma. Solar energy could power magnetic confinement systems, plasma heating methods, and fuel processing, making fusion systems cleaner and more energy efficient overall. System-level integration for a solar plasma civilization. In an integrated solar plasma energy system, sunlight is first converted into high-energy plasma where extreme conditions are needed. Plasma then serves as an intermediary that transforms solar energy into electricity, fuels, materials, and propulsion. Electricity powers everyday infrastructure, chemical fuels store energy for long-term and mobile uses, and plasma-based manufacturing closes material loops. Together, these systems form a resilient, regenerative energy economy that operates without combustion and with minimal environmental impact. Solar energy can be converted into plasma by concentrating sunlight or by using solar-generated electricity to ionize gases. Plasma then acts as a versatile energy medium that enables high-efficiency power generation, fuel synthesis, materials recycling, and advanced propulsion. While plasma itself is not an energy source, it is a powerful transformer that allows solar energy to be used in ways that are otherwise impossible, supporting a technologically advanced, sustainable civilization. Turning solar energy into plasma to power civilization. Solar energy is the most abundant and continuously available energy source accessible to humanity. Every second, the sun delivers far more energy to Earth than human civilization consumes in an entire year. The central challenge is not the availability of solar energy, but the ability to convert it into forms that can power industry, transportation, manufacturing, and long-term energy storage at planetary scale. One of the most powerful and underutilized approaches to this challenge is the use of plasma as an intermediary energy state. Plasma, the ionized state of matter, enables extreme temperatures, high energy densities, and strong electromagnetic interactions that allow solar energy to be transformed into electricity, fuels, materials, and propulsion systems far beyond the limits of conventional technologies. This essay explains how solar energy can be converted into plasma, how plasma can be controlled and sustained, and how plasma-based systems can power nearly all aspects of civilization in a clean, scalable, and regenerative manner. Plasma as an energy state and transformation medium. Plasma is a state of matter in which atoms are partially or fully ionized, meaning that electrons are no longer bound to atomic nuclei. This state forms when matter receives sufficient energy to overcome atomic binding forces. Unlike solids, liquids, or gases, plasma is electrically conductive and responds strongly to electric and magnetic fields. Because of these properties, plasma can transport energy, drive electrical currents, and enable chemical reactions that are otherwise impossible. It is essential to understand that plasma is not a primary energy source. Plasma does not generate energy unless nuclear fusion occurs. Instead, plasma is a high-energy transformation medium that allows energy from sources such as sunlight to be converted into highly useful forms. In this sense, plasma functions as a universal interface between solar radiation and the physical processes that power civilization. Concentrating solar energy to create plasma. One of the most direct ways to convert solar energy into plasma is through concentrated solar thermal systems. These systems use mirrors or lenses to collect sunlight over large areas and focus it onto a small target. This concentration dramatically increases the energy density of sunlight, raising temperatures to several thousand Kelvin or more. When a gas is exposed to such extreme temperatures, collisions between atoms become energetic enough to strip electrons from nuclei. This process ionizes the gas, turning it into plasma. The plasma can be sustained as long as solar energy continues to supply heat faster than energy is lost through radiation and expansion. Solar thermal plasma systems have a key advantage over conventional power plants because they eliminate the need for combustion. Instead of burning fuel to generate heat, they use sunlight directly to create high-temperature plasma, avoiding greenhouse gas emissions and fuel extraction entirely. Plasma-based electricity generation. Once plasma is created, it can be used to generate electricity through electromagnetic principles. Because plasma contains free-moving charged particles, its motion through a magnetic field induces electric currents. This phenomenon forms the basis of magnetohydrodynamic (MHD) power generation. In an MHD generator, hot plasma flows through a channel surrounded by strong magnetic fields. As charged particles move through the field, electrical energy is extracted directly from the plasma without the use of mechanical turbines. This allows operation at far higher temperatures than conventional steam-based power plants, improving efficiency and reducing mechanical wear. Solar-powered plasma electricity generation therefore offers a pathway to high-efficiency power production using minimal moving parts and no fossil fuels. Solar electricity-driven plasma systems. In addition to direct thermal methods, solar energy can be converted into plasma using photovoltaic systems. Solar panels convert sunlight into electricity by exciting electrons in semiconductor materials. This electricity can then be used to ionize gases using electric fields, radio frequency waves, or microwaves. Electrically sustained plasma systems offer precise control over plasma temperature, density, and composition. They can be switched on and off rapidly, scaled across a wide range of sizes, and tuned for specific applications. These systems are already used in semiconductor manufacturing, materials processing, and space propulsion, demonstrating their reliability and versatility. Although this approach introduces conversion losses, it provides unmatched flexibility and integration with existing electrical infrastructure. Plasma as a driver of solar fuel production. One of the most important roles of plasma in a solar-powered civilization is energy storage. Solar energy is intermittent, but plasma enables the conversion of sunlight into chemical fuels that store energy and stable molecular bonds. Plasma provides temperatures and energy densities high enough to break strong chemical bonds in molecules such as water, carbon dioxide, and nitrogen. In a plasma reactor, These molecules can be dissociated into reactive atoms and radicals. As the plasma cools under controlled conditions, these atoms recombine into hydrogen, synthetic hydrocarbons, ammonia, and other fuels. These fuels store solar energy in a dense, transportable form that can power aircraft, ships, heavy industry, and backup energy systems. By recycling carbon dioxide from the atmosphere or industrial emissions, plasma fuel systems can operate in a closed carbon loop, eliminating net greenhouse gas emissions. Plasma-based materials and manufacturing. Plasma enables a fundamentally new approach to manufacturing by providing extreme temperatures without combustion. Metals, ceramics, and minerals can be melted, vaporized, or atomized using solar-generated plasma. This allows smelting and refining to occur without fossil fuels. Plasma processing also enables atomic-level recycling. Waste materials can be broken down into elemental components, which can then be recombined into new products. This approach supports a circular industrial economy in which materials are reused indefinitely rather than discarded. Because plasma environments can be tightly controlled, they allow the production of ultra-pure materials essential for advanced electronics, energy systems, and scientific instruments. Plasma propulsion powered by solar energy. Plasma plays a critical role in transportation, particularly in space. Solar panels can generate electricity that ionizes a propellant gas, creating plasma. Electric and magnetic fields then accelerate the plasma to extremely high velocities, producing thrust. Plasma propulsion systems use far less propellant than chemical rockets because they achieve much higher exhaust velocities. This makes them ideal for satellites, space stations, asteroid mining, and deep space exploration. In the long term, solar-powered plasma propulsion could enable large-scale space infrastructure that supports Earth-based sustainability by providing access to extraterrestrial resources. Direct solar ionization in space plasma systems. In space environments, solar ultraviolet and X-ray radiation naturally ionize gases, creating plasma without intermediate conversion steps. Planetary ionospheres and the solar wind are examples of naturally occurring solar-driven plasmas. Future technologies may harness this direct ionization by capturing and controlling space plasmas using magnetic fields. Such systems could potentially provide power, propulsion, or radiation shielding for space habitats and spacecraft. Solar-assisted fusion plasma. Fusion represents the most energy-dense application of plasma, as it releases energy directly from atomic nuclei. While solar energy alone cannot sustain fusion reactions, it can assist fusion systems by powering plasma heating, magnetic confinement, and fuel processing. Solar-assisted fusion could reduce the external energy input required for fusion reactors, making them cleaner and more efficient. Although fusion remains a long-term goal, plasma physics developed for solar energy systems directly supports fusion research. A solar plasma civilization. In a fully integrated solar plasma energy system, sunlight is first converted into plasma where extreme energy densities are required. Plasma then transforms solar energy into electricity, fuels, materials, and propulsion. Electricity powers daily life, chemical fuels store energy for transport and industry, and plasma-based manufacturing closes material loops. Such a civilization would operate without combustion, minimize pollution, recycle materials at the atomic level, and align human industry with the fundamental processes that power stars and ecosystems. Turning solar energy into plasma does not mean powering civilization with plasma directly, but rather using plasma as a powerful intermediary that enables transformations beyond the limits of conventional technology. Through concentrated solar heating and solar-generated electricity, plasma can drive efficient power generation, fuel synthesis, materials recycling, and advanced propulsion. Together, these systems form the foundation of a clean, scalable, and regenerative energy civilization capable of supporting both planetary sustainability and space expansion. How can solar to plasma power everything in our society and tackle climate change? This question goes right to the heart of climate change and system-level energy design. Below is a comprehensive, complete sentence explanation of how solar to plasma systems could realistically power nearly all sectors of society while eliminating net greenhouse gas emissions. Written as a unified framework rather than isolated technologies. Why climate change is fundamentally an energy conversion problem. Climate change is primarily driven by the combustion of fossil fuels, which releases carbon dioxide and other greenhouse gases that were previously stored underground. Fossil fuels are used not because they are clean, but because they are dense, controllable, and versatile energy carriers. Electricity alone cannot easily replace them in aviation, shipping, heavy industry, fertilizer production, and high-temperature manufacturing. To solve climate change at the root, society needs an energy system that is abundant, clean, storable, transportable, and capable of producing extreme temperatures without combustion. Solar energy is abundant and clean, but it is intermittent and diffuse. Plasma provides the missing link by enabling solar energy to be concentrated, transformed, stored, and deployed across every sector of civilization. Solar to plasma as a universal energy conversion layer. Solar to plasma systems work by first capturing sunlight and then converting it into plasma using either concentrated solar heat or solar-generated electricity. Plasma acts as a universal energy interface because it can interact directly with electric fields, magnetic fields, chemical reactions, and materials at very high temperatures. Instead of relying on burning carbon to reach high energy densities, society uses plasma to deliver energy exactly where extreme conditions are required. This eliminates combustion while preserving industrial capability, powering electricity systems without fossil fuels. Solar plasma power generation. Concentrated solar systems can generate plasma at temperatures far above those achievable in conventional power plants. Plasma flowing through magnetic fields can generate electricity directly through magnetohydrodynamic conversion. This avoids mechanical turbines, increases efficiency, and reduces maintenance. Solar-powered plasma generators can operate continuously when paired with thermal or chemical storage systems, stabilizing electrical grids without fossil backup. Climate impact. This eliminates coal and gas power plants, which are among the largest sources of global carbon dioxide emissions, replacing fossil fuels with plasma-made solar fuels. Why fuels are still needed? Many sectors cannot rely on electricity alone. Long-distance aviation, maritime shipping, steel production, cement manufacturing, and fertilizer synthesis all require dense energy carriers or high-temperature reactions. Plasma-enabled fuel synthesis. Solar-generated plasma can break carbon dioxide in water into basic chemical components and recombine them into synthetic hydrocarbons, hydrogen, ammonia, and alcohols. These fuels store solar energy in chemical bonds and can be transported and used with existing infrastructure. Because the carbon in these fuels comes from captured carbon dioxide, their use does not increase atmospheric carbon levels. Climate impact. This replaces oil, gas, and coal while maintaining modern transportation and industry, effectively closing the carbon loop. Decarbonizing heavy industry and materials production. Plasma-based manufacturing. Steel, cement, glass, aluminum, and chemicals require extreme heat, which is currently provided by fossil fuels. Solar-generated plasma can provide these temperatures without combustion. Plasma can also directly reduce metal ores, break down waste, and synthesize new materials, enabling fully electrified and solar-powered industrial systems. Climate impact. Heavy industry accounts for a large fraction of global emissions. Plasma-based manufacturing removes fossil fuels from these processes entirely. Energy storage and grid stability through plasma chemistry. Solar energy is intermittent, but plasma enables multiple long-duration storage pathways. Energy can be stored as chemical fuels, high-temperature thermal reservoirs, or industrial feedstocks. Plasma systems can rapidly absorb excess solar energy and convert it into storable forms, then release it when demand is high. This stabilizes grids without gas-fired backup plants. Climate impact. This eliminates the need for fossil fuel peaker plants and solves one of the main challenges of renewable energy deployment. Transportation powered by solar plasma systems. Ground transportation. Electric vehicles powered by solar electricity become the dominant mode for cars and light transport. Aviation and shipping. Solar plasma-derived fuels power aircraft and ships with net zero carbon emissions. Plasma synthesis enables fuels with energy densities comparable to jet fuel but without fossil extraction. Space and high-efficiency propulsion. Solar-powered plasma thrusters enable efficient space transport, supporting satellite networks, climate monitoring, and off-planet resource use. Actively reversing climate change with plasma systems. Solar-to-plasma systems do more than stop emissions. They can actively remove carbon dioxide from the atmosphere. Plasma reactors can process captured carbon dioxide into stable materials, fuels, or long-lived products, combined with biological systems such as reforestation and soil carbon sequestration. This creates a net negative carbon economy. System-level transformation of society. A solar plasma society reorganizes energy flows around abundance rather than scarcity. Instead of extracting ancient carbon, civilization uses real-time solar energy to power all processes. Cities become centers of energy conversion rather than consumption. Industry becomes circular rather than extractive. Waste becomes feedstock. Carbon becomes a managed material rather than a pollutant. Why this approach is realistic, not speculative. Most of the underlying technologies already exist in partial form: concentrated solar power, plasma reactors, magnetohydrodynamics, synthetic fuels, and plasma manufacturing are all demonstrated technologies. The challenge is integration, scaling, and political will, not basic physics. Solar to plasma systems can power nearly every sector of society by providing a clean, high-energy intermediary that replaces fossil fuel combustion. By generating electricity, producing carbon-neutral fuels, decarbonizing heavy industry, stabilizing energy grids, and enabling carbon removal, solar plasma systems directly address the root causes of climate change. Rather than reducing civilization's capabilities, this approach preserves and enhances them while aligning human industry with the fundamental energy processes of the sun. Solar energy capture technologies. How photovoltaic systems work. Photovoltaic solar panels generate electricity by absorbing sunlight in semiconductor materials such as silicon. When photons strike the material, they transfer energy to electrons, allowing those electrons to move freely across an internal electric field. This movement of electrons creates a direct electric current. The electricity produced can be used immediately or routed into plasma generating systems, storage systems, or electrical grids. Photovoltaic systems are efficient at producing electricity, but do not directly produce high temperatures or dense energy states, which is why they are often paired with plasma technologies. How concentrated solar power systems work. Concentrated solar power systems use mirrors or lenses to collect sunlight over a large area and focus it onto a much smaller receiver. This concentration increases the intensity of solar energy by hundreds or thousands of times. When sunlight is concentrated in this way, it produces extremely high temperatures, often exceeding several thousand degrees Celsius. These temperatures are sufficient to heat gases until they become ionized, forming plasma. Concentrated solar systems therefore convert diffuse solar radiation into dense thermal energy, capable of driving industrial-scale plasma processes. Plasma generation technologies. How thermal plasma is created using solar heat. Thermal plasma forms when a gas is heated to extremely high temperatures so that collisions between particles become energetic enough to strip electrons from atoms. Concentrated solar heat raises the kinetic energy of gas particles until ionization occurs. As long as solar energy continues to supply heat, the plasma remains stable. Thermal plasma is useful for applications requiring extreme heat, such as material processing, fuel synthesis, and high-efficiency electricity generation. How electrically generated plasma works. Electrically generated plasma is created by applying strong electric or electromagnetic fields to a gas. When voltage is applied, free electrons accelerate and collide with neutral atoms, ionizing them and creating more free electrons in a cascading process. Radio frequency and microwave systems can sustain plasma without direct electrical contact. Solar-generated electricity powers these plasma systems, allowing precise control over plasma temperature, density, and chemistry. Magnetohydrodynamic electricity generation. How plasma is converted into electricity. Magnetohydrodynamic generators work by passing electrically conductive plasma through a magnetic field. As charged particles in the plasma move through the field, they experience a force that separates positive and negative charges. Electrodes or induction coils capture this charge separation as electrical current. This process converts thermal and kinetic energy directly into electricity without mechanical turbines. Because there are no moving solid parts exposed to extreme heat, magnetohydrodynamic generators can operate at temperatures far higher than conventional power plants. Why this improves efficiency and reduces emissions. Higher operating temperatures increase thermodynamic efficiency, meaning more of the captured solar energy is converted into usable electricity. Because no fuel is burned, the process produces no carbon dioxide or air pollution. Plasma-based energy storage and fuel synthesis. How plasma splits stable molecules. Plasma contains highly energetic electrons and ions that collide with molecules such as water, carbon dioxide, and nitrogen. These collisions break strong chemical bonds that are difficult to break using conventional heat or catalysts. The plasma effectively dissociates these molecules into atoms and reactive fragments. How synthetic fuels are formed. After dissociation, the reactive atoms are cooled and recombined under controlled conditions. Hydrogen atoms form molecular hydrogen. Carbon and hydrogen combine into hydrocarbons. Nitrogen and hydrogen form ammonia. These products store energy in chemical bonds that originated from sunlight. Because the carbon source is atmospheric or recycled carbon dioxide, burning or using these fuels does not increase net greenhouse gas concentrations. Plasma-based industrial manufacturing. How plasma replaces fossil fuel heat. Many industrial processes require temperatures above what electric resistance heating can efficiently provide. Plasma systems can deliver temperatures exceeding 10,000 degrees Celsius without combustion. Solar-generated plasma therefore replaces coal, oil, and gas in steelmaking, cement production, and chemical manufacturing. How plasma enables circular material use. Plasma can vaporize or atomize waste materials, separating them into elemental components. These elements can then be reused to manufacture new products. This enables closed-loop material cycles that dramatically reduce mining, waste, and environmental damage. Grid stability and energy buffering. How plasma supports renewable grids. Plasma systems can rapidly absorb excess solar electricity by converting it into heat, chemical fuels, or industrial products. When solar generation decreases, stored fuels or thermal energy can be converted back into electricity. This flexibility allows electrical grids to operate entirely on renewable energy without fossil fuel backup. Transportation powered by solar plasma systems. How ground transportation is powered. Electric vehicles use solar-generated electricity stored in batteries. Plasma technologies indirectly support this system by stabilizing grids and producing materials for batteries and infrastructure. How aviation and shipping are powered. Aircraft and ships require dense fuels. Plasma-synthesized fuels provide energy densities similar to conventional fuels, but are produced using solar energy and recycled carbon. These fuels function in existing engines with minimal modification. How plasma propulsion works. Plasma propulsion systems ionize a propellant gas and accelerate it using electric and magnetic fields. The momentum of the expelled ions produces thrust. Solar panels provide the electricity required for ionization and acceleration. Carbon capture and climate repair. How plasma processes captured carbon dioxide. Carbon dioxide captured from air or industrial sources is fed into plasma reactors. The plasma breaks the molecule apart into carbon monoxide and oxygen or elemental carbon. These components are reused to make fuels, building materials, or long-lived carbon products. This converts carbon dioxide from a waste product into a managed industrial resource. System-level integration. In a solar-to-plasma system, solar energy is first captured as electricity or heat. Plasma then serves as the high-energy transformation stage that enables electricity generation, fuel synthesis, industrial heat, material recycling, and propulsion. Each output feeds other parts of society, creating a tightly integrated, low-waste energy economy. Instead of extracting ancient carbon, society continuously converts sunlight into usable energy forms in real time. Why this addresses climate change comprehensively. Solar-to-plasma technologies eliminate fossil fuel combustion across electricity generation, industry, transportation, and materials production. They also enable carbon dioxide removal and reuse. By addressing both energy supply and carbon management, these technologies tackle climate change at its root rather than treating symptoms. Solar-to-plasma technologies work by using solar energy to create ionized matter that enables high-temperature processes, direct electricity generation, chemical fuel synthesis, industrial manufacturing, and carbon recycling without combustion. Plasma functions as a universal energy transformation layer that allows solar energy to power all major sectors of society while eliminating net greenhouse gas emissions. Solar-to-plasma energy systems, physics, feasibility, and revolutionary applications. Understanding the plasma vision. The question of converting solar energy into plasma to power civilization invites us into fascinating territory at the intersection of fundamental physics, advanced energy systems, and transformative possibilities. However, we must first clarify what this means, because turning solar energy into plasma and using plasma to power everything involves several distinct concepts that need unpacking. Plasma, often called the fourth state of matter, is ionized gas where electrons have been stripped from atoms, creating a collection of charged particles. Plasma exists in nature and stars, including our sun, lightning, auroras, and flames. It also appears in human technologies including fluorescent lights, plasma TVs, now mostly obsolete, semiconductor manufacturing, and fusion reactors. Plasma has extraordinary properties. It conducts electricity, responds to magnetic fields, can reach extreme temperatures, and enables nuclear fusion. The question could mean several different things: using solar energy to create plasma that somehow improves energy conversion, storage, or transmission; harnessing the sun's plasma, solar wind directly as an energy source, creating fusion plasma powered by solar-generated electricity to achieve sustainable fusion power, using plasma-based technologies throughout energy systems powered by solar electricity, transmitting energy as plasma rather than conventional electricity. Each interpretation leads to different technologies and implications. This essay will explore all of these pathways, examining the physics involved, current technological state, theoretical possibilities, practical challenges, and potential revolutionary applications. We'll discover that while some plasma-based energy concepts are scientifically sound and technically achievable, others face fundamental physical limitations that may be insurmountable. The physics of plasma and energy conversion. What is plasma and why does it matter for energy? To understand plasma's potential role in energy systems, we must understand what plasma is at a fundamental level and what special properties it possesses. Creating plasma. Plasma forms when energy is added to gas, usually through heating, electromagnetic fields, or particle bombardment, until electrons gain enough energy to escape atomic nuclei. The resulting mixture of free electrons, positive ions, and neutral atoms exhibits collective behavior dramatically different from ordinary gas. The energy required to ionize gas depends on the element and degree of ionization. Hydrogen, the simplest element, requires 13.6 electron volts, eV, to ionize completely. In practical terms, this means heating hydrogen to temperatures around 10,000 degrees Celsius, 18,000 degrees Fahrenheit, will partially ionize it, creating plasma. Full ionization of heavier elements requires even higher temperatures, millions of degrees for some elements. Plasma properties. Electrical conductivity. Free electrons and ions carry electric current far more effectively than ordinary matter, making plasma excellent electrical conductor. Magnetic responsiveness. Charged particles in plasma respond to magnetic fields, allowing plasma to be confined, shaped, and controlled magnetically. Collective behavior. Plasma particles interact through long-range electromagnetic forces, creating waves, instabilities, and organized structures. Energy density. Hot plasma contains enormous energy. Fusion plasma at 100 million degrees Celsius stores extraordinary energy per unit volume. Radiation. Hot plasma emits electromagnetic radiation across the spectrum from radio waves to X-rays, depending on temperature. Types of plasma. Plasmas vary enormously in temperature, density, and degree of ionization. Cold plasma. Non-thermal plasma. Electrons are hot, thousands of degrees, but ions remain cool, room temperature. Found in fluorescent lights, plasma TVs, and industrial processing. The bulk gas temperature remains low while electrons have high energy. Thermal plasma. Electrons and ions reach similar high temperatures, thousands to millions of degrees. Found in arc welders, plasma torches, and fusion experiments. Fusion plasma. Extremely hot, 150 million degrees Celsius and fully ionized, necessary for nuclear fusion reactions. Astrophysical plasma. Found in stars, interstellar medium, and space environments, varying wildly in properties. Energy in plasma. How energy is stored and released. Understanding how energy exists in plasma illuminates why it might be useful, or not, for energy systems. Energy storage mechanisms. Plasma stores energy in multiple forms. Thermal energy, the kinetic energy of particles moving at high velocities. Temperature measures average kinetic energy. Hot plasma has particles moving at extraordinary speeds. Ionization energy, the energy required to strip electrons from atoms, stored in the ionized state and released when ions recombine with electrons. Magnetic energy, plasma confined by magnetic fields stores energy in the magnetic field configuration. Radiation energy, hot plasma emits electromagnetic radiation carrying energy away. Energy extraction, getting useful energy from plasma faces fundamental challenges. Thermodynamic efficiency, converting thermal energy to electricity follows Carnot efficiency limits. Maximum efficiency equals 1, T cold T hot. Even with plasma at millions of degrees, practical cold side temperatures limit efficiency. Radiation losses, hot plasma radiates energy, particularly at high densities. For fusion, radiation loss scales with density squared while fusion power scales with density squared, creating optimization challenges. Confinement energy cost. Magnetic confinement requires energy to generate fields. Strong fields need superconducting magnets with cryogenic cooling, significant energy investment. Thermalization. Converting plasma thermal energy to electricity typically requires conventional heat exchangers and turbines, adding complexity and losses. The fundamental challenge: creating and maintaining plasma typically requires more energy than you can practically extract from it, unless the plasma is generating additional energy through nuclear reactions, fusion, or serving as intermediary for energy conversion rather than storage medium. This means that proposals to store energy as plasma face fundamental problems. The energy cost of creating and maintaining plasma generally exceeds any benefit from its plasma state. Plasma makes sense only when it enables otherwise impossible reactions, fusion. It provides unique processing capabilities justifying energy cost. It occurs naturally and we can harvest it. Solar wind. It improves energy conversion efficiency beyond conventional methods. Solar plasma conversion pathways. Direct solar to plasma conversion, concentrated solar thermal plasma. The most straightforward interpretation of converting solar energy to plasma is using concentrated solar thermal energy to create plasma directly. Concentrated solar plasma systems, solar concentrators, mirrors or lenses, focus sunlight to achieve extreme temperatures. Standard concentrated solar power systems reach 400 to 600 degrees Celsius. Advanced systems using multiple concentration stages can exceed 1000 degrees Celsius. At temperatures above 3000 to 4000 degrees Celsius, gases begin ionizing, creating plasma. The physics: sunlight arriving at Earth's surface delivers roughly 1000 watts per square meter. Concentrating this by 1000 times produces 1 megawatt per square meter, enough to reach temperatures that vaporize and ionize most materials. Concentration ratios of 10,000 times or higher are achievable with precise optics, reaching temperatures where plasma forms. Applications: materials processing. Plasma created by concentrated solar energy can process materials, destroy waste, or produce chemicals at very high temperatures. Thermal energy storage. Very high temperature thermal storage using materials that remain stable above 1000 degrees Celsius, potentially including plasma-compatible ceramics. Thermochemical reactions. High temperature chemical reactions including hydrogen production from water splitting, CO2 reduction, or synthesis of materials requiring extreme conditions. Research examples: Swiss Federal Institute of Technology, ETH Zurich, operates solar furnaces reaching 3000 degrees Celsius using concentrated sunlight. The Paul Scherrer Institute demonstrated solar thermochemical fuel production at temperatures exceeding 1500 degrees Celsius. Various research facilities explore using concentrated solar to drive high-temperature chemical processes. Practical limitations: creating plasma with concentrated solar faces significant challenges. Intermittency: solar concentration only works during clear daytime conditions, requiring thermal storage for continuous operation. Efficiency: converting plasma thermal energy back to electricity involves conventional thermodynamic cycles with inherent efficiency limits. Materials: containing plasma requires materials that withstand extreme temperatures, radiation, and chemical attack. Scale: achieving the concentration ratios and optical precision needed for consistent plasma generation at large scale is technically demanding. Economic viability: the complexity of creating, containing, and utilizing solar plasma must justify cost compared to simpler solar technologies. While technically possible to create plasma using concentrated solar energy, this approach faces significant practical and economic challenges. The resulting plasma is useful primarily for specialized high-temperature processes rather than general power generation. Because converting the plasma's thermal energy back to electricity typically has lower efficiency than direct photovoltaic conversion or conventional concentrated solar power. Photovoltaic to plasma, using solar electricity to generate plasma. A more practical interpretation is using solar-generated electricity to create plasma for various applications. How this works: photovoltaic panels convert sunlight to electricity with 15 to 25% efficiency. Commercially available panels, or 40% plus advanced multi-junction cells. This electricity can then power plasma generators through various methods. Electrical discharge: applying high voltage across gas creates electric arc plasma. Radio frequency, RF heating: electromagnetic waves couple energy into gas, accelerating electrons and creating plasma. Microwave plasma, similar to RF but at microwave frequencies. Laser-induced plasma: high-intensity lasers ionize gas, creating plasma. Applications: this pathway makes sense for applications where plasma provides unique capabilities. Industrial processing: plasma cutting and welding, electric arc plasma cuts or welds metal with precision and speed. Surface treatment: plasma modifies material surfaces, adding coatings, cleaning, or changing properties. Semiconductor manufacturing. Plasma etching creates nanoscale features on silicon wafers. Waste treatment. Plasma gasification converts waste to syngas at temperatures that destroy toxic compounds. Hydrogen production. Plasma water splitting, using plasma to dissociate water into hydrogen and oxygen. Research shows this can potentially be more efficient than conventional electrolysis under certain conditions. Plasma reforming, breaking down hydrocarbons into hydrogen using plasma, potentially more efficient than traditional steam reforming. Agricultural applications. Plasma-activated water, treating water with plasma creates reactive nitrogen species that can enhance plant growth, potentially replacing some fertilizers. Seed treatment. Brief plasma exposure can improve germination rates and disease resistance. Food preservation. Cold plasma can sterilize food surfaces without heat, extending shelf life. Medical applications. Plasma sterilization. Cold atmospheric plasma can sterilize medical instruments and surfaces. Plasma medicine. Emerging field using cold plasma for wound healing, cancer treatment, and dental applications. The efficiency question. For most of these applications, the question isn't whether solar-powered plasma generation is possible, it clearly is, but whether it's the most efficient use of solar energy. Generally, the answer is sometimes. For applications requiring plasma's unique properties, precision etching, specialty chemical reactions, using solar electricity to generate plasma makes sense if it replaces fossil fuel generated electricity. For applications where plasma is one option among many, efficiency comparisons with alternatives determine viability. For bulk energy conversion, generating electricity, creating plasma as intermediate step almost always reduces efficiency compared to direct conversion. Fusion energy, the ultimate solar plasma system, solar energy to fusion plasma, completing the cycle. Perhaps the most profound interpretation of using solar energy to power plasma is using solar-generated electricity to achieve nuclear fusion, essentially recreating the sun's energy generation process here on Earth. The vision: the sun generates energy through nuclear fusion, hydrogen atoms fusing into helium, releasing enormous energy according to E=mc². Achieving controlled fusion on Earth requires creating plasma at temperatures of 150 million degrees Celsius, hotter than the sun's core, where hydrogen isotopes overcome electromagnetic repulsion and fuse together. The irony and elegance is compelling, using energy from the sun's fusion reactions, captured as solar electricity to create conditions that replicate those reactions here on Earth, achieving self-sustaining fusion that then provides far more energy than the solar input required. Fusion fundamentals: the most promising fusion reaction for terrestrial power uses deuterium, heavy hydrogen with 1 neutron, and tritium, heavier hydrogen with 2 neutrons, D plus T helium, 4 plus neutron plus 17.6 MeV of energy. This reaction is easiest because it occurs at lowest temperatures, 5100 million degrees Celsius, and has highest cross-section probability of occurring among candidate fusion reactions. Creating fusion plasma, achieving fusion requires extreme temperature, 150 million degrees Celsius, to give particles enough kinetic energy to overcome electrostatic repulsion. Sufficient density, enough particles in small volume to make collisions frequent. Adequate confinement time, holding plasma together long enough for fusion reactions to occur before particles escape. The fundamental challenge is that no material can contain plasma at these temperatures. Any contact with walls instantly cools the plasma. Two primary approaches overcome this: magnetic confinement fusion, MCF, using powerful magnetic fields to confine plasma without physical contact. The leading design is the tokamak, a donut-shaped chamber with magnetic coils that twist plasma and enclosed magnetic field lines that trap particles. Current status: ITER, International Thermonuclear Experimental Reactor, under construction in France's humanity's largest fusion experiment. It will use superconducting magnets generating 11.8 Tesla fields to confine plasma in 840 cubic meter volume. SPARC, MIT Commonwealth Fusion Systems, is smaller tokamak using high-temperature superconductors, HTS, enabling stronger magnetic fields, 12 Tesla, in compact design. Demo, planned successor to ITER, would be the first fusion reactor actually connected to electrical grid, planned for 2050s. Multiple private companies: Commonwealth Fusion, TE Technologies, General Fusion, Helion, pursue various magnetic confinement approaches. Inertial confinement fusion, ICF, using powerful lasers or particle beams to compress small fuel pellets to extreme densities and temperatures where fusion occurs during brief moment of peak compression. Current status: National Ignition Facility, NIF, in December 2022, achieved fusion ignition, the first controlled fusion experiment where fusion energy output exceeded laser energy input. This historic milestone proved fusion can work, though the facility's overall energy balance remains negative. Lasers require more energy than fusion produces. Multiple companies pursue ICF approaches including laser-based, first light fusion, and pulse power, Sandia's machine, solar-powered fusion, the complete system. Imagine a fusion power plant where solar farms generate electricity using photovoltaics, batteries, or other storage provide consistent power supply. Fusion reactor uses this electricity to generate magnetic fields, for magnetic confinement power heating systems, neutral beam injection, RF heating, microwave heating, run cryogenic systems, cooling, superconducting magnets, operate auxiliary systems. Fusion reactions in plasma generate far more energy than the solar derived input. Energy extraction converts fusion energy to electricity, with net electricity output far exceeding solar input. The energy arithmetic. Once fusion achieves ignition, fusion reactions producing more energy than required to maintain plasma, the energy multiplication can be substantial. Q factor measures energy multiplication. Q equals fusion power output. External heating power at our targets Q10, meaning 50 megawatts of heating produces 500 megawatts of fusion power. Power plants need Q2030 for economic viability when considering inefficiencies in energy extraction and recirculation. The vision is solar panel generates 1 kilowatt-hour of electricity. Fusion system converts to 1030 kilowatts-hour of electricity out. Net gain of 929 kilowatts-hour per kWh of solar input. Current reality check. Despite 70-plus years of fusion research and billions invested, no facility has achieved net energy gain accounting for all energy inputs, though NIF achieved physics ignition. Engineering challenges remain immense. Materials that withstand neutron bombardment, tritium breeding and handling, plasma stability and control. Energy extraction timelines continually slip. Fusion has been 30 years away for 70 years. Economic viability unproven. Even successful fusion may not be cheaper than renewables plus storage. Why pursue solar fusion integration? If fusion becomes viable, solar fusion integration offers several advantages. Renewable bootstrapping. Using renewable energy to start fusion avoids fossil fuel dependency. Hybrid systems. Solar provides baseline power while fusion provides high density power for industrial processes or during low renewable periods. Desert fusion plants. Locating fusion facilities in deserts with abundant solar for startup and auxiliary power. Closed carbon cycle. The entire energy system from solar bootstrap to fusion operation produces no carbon emissions. Timeline reality. Optimistic projections put first commercial fusion power in 2030s, negative 2040s. More conservative estimates suggest 2050s or later. Many physicists remain skeptical that fusion will ever be economically competitive with advancing renewables and storage. The dream of solar-powered fusion remains aspirational, but represents the ultimate expression of using solar energy to create plasma that powers civilization. Space-based plasma energy. Harvesting solar wind. The solar wind, natural plasma from the sun. The sun continuously ejects plasma, the solar wind, that streams through solar system at 400 to 750 kilometers second. This represents enormous energy flow that, if harnessed, could power civilization many times over. Solar wind composition and energy. The solar wind consists of charged particles, mostly protons and electrons accelerated by the sun's corona. At Earth's orbit, particle density, 510 particles per cubic centimeter. Velocity, 400 to 750 kilometers second. Temperature, 100,000 Kelvin. Magnetic field, 510 nanotesla. The kinetic energy flux is approximately 13 watts per square meter at Earth's orbit, far less than sunlight, 1,367 watts per square meter, but still representing significant total power flow. Harvesting solar wind. Theoretical approaches. Magnetic sails, using large-scale magnetic fields to deflect solar wind particles, transferring their momentum and potentially capturing energy. The concept resembles how Earth's magnetosphere deflects solar wind. A magnetic sail would generate powerful magnetic field using superconducting coils. Extend field lines over large area, potentially hundreds of kilometers. Deflect solar wind particles, transferring momentum. Potentially extract electrical energy from induced currents. Plasma collectors, devices that directly collect solar wind particles and extract their kinetic energy. This could involve charged grids that attract and collect ions. Magnetic funnels that concentrate particles. Direct energy conversion from particle kinetic energy to electricity. Reality check. While theoretically possible, Solar wind energy harvesting faces enormous challenges. Energy density. Solar wind carries 1,000 times less energy than sunlight at Earth's orbit collection area. Capturing meaningful power requires structures hundreds of kilometers across. Engineering, building, deploying, and maintaining such structures in space far exceeds current capabilities. Energy transmission. Getting captured energy back to Earth requires wireless power transmission or enormous batteries for transport. Economics. Cost per watt astronomical compared to terrestrial solar current applications. Solar wind harvesting remains firmly in theoretical realm, though understanding solar wind is crucial for protecting satellites from space weather, planning missions beyond Earth's magnetosphere, understanding plasma physics, protecting future Mars colonies. Mars lacks protective magnetosphere. The energy potential exists, but practical harvesting remains science fiction with no clear path to viability. Part 5. Plasma-based energy transmission and distribution. Wireless power transmission via plasma. One interpretation of using plasma to power everything might involve transmitting energy through plasma rather than conventional conductors. Plasma as conducting channel. Plasma's electrical conductivity far exceeds copper or aluminum. Theoretically, plasma channels could transmit power wirelessly. Lightning-inspired transmission. Lightning demonstrates that atmosphere can conduct electricity when ionized. Controlled plasma channels could, in theory, transmit power through air. Proposed mechanisms. Laser-induced plasma channels. High-power lasers create ionized channels through which electrical current flows. Microwave-sustained plasma. Microwave beams create and maintain plasma channels for power transmission. Charged particle beams. Beams of electrons or ions carry electrical current through space or atmosphere. Tesla's vision. Nikola Tesla experimented with wireless power transmission, though his approach used resonant electromagnetic coupling rather than plasma channels. Modern interpretations sometimes invoke plasma physics. Fundamental problems. Plasma-based wireless power transmission faces insurmountable challenges for general use. Energy loss. Creating and maintaining plasma requires more energy than it transmits except over very short distances. Atmospheric breakdown. Sustained high-power plasma in atmosphere creates safety hazards, EMI, ozone, and NOx pollution. Directionality. Plasma channels are difficult to direct precisely over long distances. Efficiency. Resistive losses, ionization energy costs, and radiation losses make plasma transmission vastly less efficient than conventional wires or even conventional wireless power. Inductive, capacitive, or microwave safety. High-energy plasma poses extreme danger to anything in its path. Niche applications. Plasma-based power transmission might work for specific applications. Spacecraft propulsion. Plasma thrusters using solar-generated electricity create ionized plasma for propulsion. Short-distance industrial processes. Plasma torches transmit electrical energy as plasma over centimeters for cutting or welding. Laboratory experiments. Studying plasma physics requires plasma power transmission over small scales for general power distribution. Plasma transmission is dramatically inferior to conventional conductors, wires, or established wireless methods. Inductive coupling for short range, microwaves for long range. The energy cost of creating plasma vastly outweighs any benefit. Practical plasma applications in solar-powered systems, where plasma actually makes sense. Rather than fantasizing about plasma as universal energy medium, let's examine where plasma technologies legitimately enhance solar-powered systems. Plasma-enhanced solar cell manufacturing. Plasma processes are essential in producing modern solar cells. Plasma-enhanced chemical vapor deposition, PECVD, deposits thin films of silicon nitride, and other materials on solar cells, creates anti-reflective coatings, improving light absorption, enables production of thin film solar cells. Plasma etching creates precise surface textures that trap light patterns. Semiconductor layers with nanoscale precision, essential for high-efficiency heterojunction solar cells. Economic impact. These plasma processes are established, economical, and essential for modern solar cell production. They represent sensible use of plasma technology in solar energy systems. Plasma gasification of waste using solar energy. Plasma gasification uses extremely high temperatures, 4,000 to 7,000 degrees Celsius, from electric arc plasma to convert waste to syngas. Process. Waste enters plasma reactor. Electric arc creates plasma at extreme temperature. Organic materials break down to syngas, H2 and company, and organic materials melt to glassy slag. Syngas can generate electricity or produce chemical. Solar integration. Powering plasma gasification with solar electricity creates closed-loop waste-to-energy system. Solar panels generate electricity. Plasma reactor processes waste syngas provides dispatchable power. When solar isn't available, toxic waste is destroyed. Not buried status. Commercial plasma gasification exists. Westinghouse Plasma, Hitachi Metals, others. Solar integration is proposed but not widely implemented. Economics currently favor fossil-powered systems, but environmental regulations and renewable energy cost declines improve viability. Solar-powered plasma water treatment. Plasma can disinfect water and break down contaminants. Non-thermal plasma in water creates reactive oxygen in nitrogen species, destroys bacteria, viruses, and parasites, breaks down pharmaceuticals, pesticides, and other pollutants, operates at near room temperature. Solar integration, off-grid water treatment using solar-powered plasma generators, disaster relief in remote communities, agricultural water treatment for irrigation status. Laboratory and pilot-scale demonstrations show effectiveness. Commercial systems emerging. Energy requirements are modest, making solar power viable. Plasma-assisted agriculture with solar power. Emerging applications use plasma to enhance agriculture. Plasma-activated water, PA, exposing water to plasma creates reactive nitrogen species. PA irrigation enhances plant growth, potentially reduces fertilizer needs, can control soil pathogens. Plasma seed treatment. Brief plasma exposure modifies seed surfaces, improves germination and disease resistance, requires minimal energy. Proceeds solar integration. Small-scale plasma systems powered by portable solar panels. Farmer accessible technology for sustainable agriculture, off-grid operation in remote agricultural areas. Status: active research with promising results. Some commercial systems available. This represents practical near-term application of solar plasma integration. Plasma-driven chemical synthesis. Plasma enables chemical reactions impossible or inefficient with conventional methods. Ammonia synthesis. Conventional Haber-Bosch process requires high pressure and temperature. Plasma-assisted ammonia synthesis works at lower pressure and temperature, can use renewable electricity efficiently, enables distributed ammonia production. CO2 reduction. Plasma can convert CO2 to CO and O2. CO can then be converted to fuels or chemicals, potentially enables carbon recycling. Solar integration. Solar electricity powers plasma reactors for green chemical production, enables local production, reducing transport emissions, matches intermittent solar with batch chemical production. Status: research stage with improving efficiencies. Several startups pursuing plasma ammonia synthesis. Economics improving as renewable electricity cost decline. Revolutionary future possibilities. Speculative but physically plausible plasma technologies. Moving beyond current capabilities to explore what might be possible with advanced technology. Atmospheric plasma shields for disaster mitigation. Concept: using plasma to modify atmospheric conditions, potentially deflecting hurricanes, suppressing wildfires, or managing severe weather. Physics: plasma responds to electromagnetic fields and can generate thermal updrafts, create ion channels, or modify electrical properties of atmosphere. Challenges: energy requirements would be astronomical, unintended consequences and environmental impacts unknown, control and prediction of complex atmospheric systems, international governance and military implications. Verdict: theoretically possible but practically implausible with foreseeable technology. Energy requirements likely exceed benefit. Plasma-based atmospheric carbon capture. Concept: using plasma to convert atmospheric CO2 to useful products or solid carbon. Physics: plasma can dissociate CO2 molecules, creating CO and O. The CO can then be converted to fuels or materials. Advantages: can process low concentration CO2, atmosphere is 0.04% CO2, potentially more efficient than conventional direct air capture, enables carbon negative fuel production. Status: research underway at multiple institutions. Some promising efficiency results, still far from commercial scale. Verdict: plausible pathway that deserves continued research, could become significant if efficiencies improve and renewable energy becomes cheap enough. Space-based solar plasma synthesis. Concept: manufacturing materials or chemicals in space using concentrated solar energy, creating plasma. Advantages: unlimited concentrated solar in space, no atmosphere, microgravity enables novel processes, no atmospheric pollution concerns, can process asteroid materials. Applications: producing ultra-pure materials for electronics, synthesizing propellants for spacecraft, manufacturing structural components for space infrastructure. Status: entirely conceptual, no concrete plans or near-term missions. Verdict: makes scientific sense but requires space infrastructure far beyond current capabilities. Relevant for long-term space colonization but not Earth energy needs. Quantum plasma states for energy storage. Concept: using exotic plasma states, potentially quantum plasmas at ultra-low temperatures or ultra-high densities, for energy storage with unprecedented density. Physics: degenerate plasmas where quantum effects dominate behavior might enable novel energy storage mechanisms. Challenges: largely theoretical, quantum plasmas are subject of ongoing research. Creating and maintaining such states requires extreme conditions. Energy extraction mechanisms unclear, may violate no free lunch thermodynamic principles. Verdict: interesting physics but no clear path to practical energy storage. Highly speculative. Why plasma isn't the answer for everything. Fundamental limitations. After exploring various plasma energy concepts, we must confront fundamental reasons why plasma won't revolutionize energy systems for most applications. Thermodynamic constraints. The second law of thermodynamics constrains all energy conversion. Creating plasma typically requires high-quality electrical or electromagnetic energy. Extracting useful energy from plasma, usually as heat, proceeds through conventional thermodynamic cycles with inherent efficiency limits. The conversion electrical plasma heat mechanical electrical typically loses more energy than direct electrical mechanical. Energy cost of ionization. Creating plasma requires energy to strip electrons from atoms. The ionization energy. For most gases, this is substantial. Hydrogen, 13.6 eV per atom. Helium, 24.6 eV air, mostly nitrogen, 14.5 eV. This energy must be supplied and is only recovered if plasma subsequently releases more energy, fusion, or performs work that couldn't be done otherwise. Specialized processing. Confinement challenges. Plasma wants to expand, cool, and recombine. Confining it requires magnetic fields, requiring energy, physical containment, limiting temperature, continuous energy input, replacing radiation and conduction losses. The energy overhead of confinement often exceeds any benefit from the plasma state. Radiation and energy loss. Hot plasma radiates energy as electromagnetic radiation. The radiated power scales with temperature to the fourth power, Stefan-Boltzmann law for blackbody radiation, and additionally as density squared for Bremsstrahlung radiation. This radiation carries energy away, requiring continuous input to maintain plasma state. Material compatibility. Plasma at substantial temperatures and densities damages most materials through thermal stress and ablation particle bombardment, causing sputtering, neutron damage. For fusion plasma, chemical reactions. This limits practical containment options and shortens component lifetimes. Economic reality. For plasma technology to be economically viable, it must either enable otherwise impossible processes, fusion, specialty manufacturing, provide superior performance justifying higher cost, reduce total system cost despite plasma overhead. For bulk energy conversion, transmission, and storage, plasma adds cost and complexity without providing benefits. Conventional technologies, wires for transmission, batteries or pumped hydro for storage, turbines for conversion, are simpler, cheaper, and more efficient. Where conventional solutions win. For most energy applications, conventional non-plasma technologies are superior. Energy generation. Photovoltaics directly convert sunlight to electricity more efficiently than solar plasma electricity. Wind turbines directly convert wind to electricity. Conventional solar thermal uses molten salt, not plasma, for thermal storage. Energy storage. Batteries store electricity directly without intermediate plasma step. Pumped hydro stores gravitational potential energy. Compressed air stores mechanical energy. Thermal storage uses solid or liquid materials, not plasma. Energy transmission. Copper and aluminum conductors transmit electricity efficiently and reliably. High voltage DC for long distance reduces losses. Superconducting cables, if needed, don't require plasma. Energy conversion. Electric motors convert electricity to mechanical power with 90% plus efficiency. Heat pumps move thermal energy efficiently. Conventional turbines convert heat to mechanical power. Plasma adds unnecessary complexity to these well-optimized systems. Practical path forward. Sensible integration of solar and plasma technologies. Rather than pursuing plasma as universal energy solution, we should focus on applications where plasma provides genuine advantages. Fusion energy. Continue investing in fusion research with understanding that success is uncertain and decades away. Multiple approaches. Magnetic confinement, inertial confinement, alternative concepts. should be pursued. Even successful fusion may not be economically competitive with mature renewables. Fusion could be transformative for space exploration, even if not economical for terrestrial power. Specialized manufacturing expands solar-powered plasma applications in semiconductor fabrication, already established advanced material synthesis, waste treatment and recycling, chemical production where plasma enables superior processes, agricultural innovation, develop and deploy plasma-activated water systems for sustainable agriculture, plasma seed treatment technologies, solar-powered plasma systems for off-grid agricultural use, water treatment, scale-up solar-powered plasma water treatment for disaster relief and humanitarian applications, remote communities without conventional infrastructure, agricultural water management, specialized contamination remediation, chemical synthesis, support research and development on plasma-assisted ammonia synthesis for green fertilizer, CO2 conversion to fuels and chemicals, plasma-driven nitrogen fixation for agriculture, distributed chemical production using intermittent renewable power. Plasma's real role in solar-powered civilization. The question, how can we turn solar energy into plasma to power everything, contains an appealing vision, harnessing the exotic fourth state of matter to revolutionize energy systems. The reality is more nuanced and, in some ways, more interesting than the science fiction vision. Plasma is not a miracle energy medium. Creating and maintaining plasma typically requires more energy than can be practically extracted, unless the plasma enables nuclear fusion or specialized processes impossible by other means. Solar to plasma conversion is possible but rarely advantageous. We can create plasma using concentrated solar thermal energy or solar-generated electricity, but for most applications, this adds unnecessary complexity and reduces efficiency. Fusion remains the grand vision, using solar energy to bootstrap fusion reactors that then generate far more power than the solar input, represents the ultimate expression of solar plasma integration. This remains decades away and faces both technical and economic uncertainties. Niche applications show promise: plasma technologies for manufacturing, semiconductors, materials processing, agriculture, plasma-activated water, seed treatment, water treatment, waste gasification, and chemical synthesis represent sensible near-term applications where plasma provides unique capabilities. Space plasma remains largely inaccessible. Harvesting solar wind or using space-based plasma systems faces enormous engineering challenges and offers little advantage over conventional space solar power approaches. Wireless plasma power transmission is impractical. Despite its appeal, transmitting power through plasma channels is less efficient, less safe, and more expensive than conventional wires or established wireless power methods. The practical vision, rather than plasma powering everything, a realistic solar-powered civilization includes photovoltaics and wind providing bulk electricity, batteries and other storage handling intermittency, conventional electrical infrastructure distributing power, plasma technologies serving specialized roles, semiconductor manufacturing, advanced materials, waste treatment, chemical synthesis, water purification, and agricultural enhancement, fusion power, potentially, eventually providing dense, clean baseload power for industrial processes and locations where renewables are insufficient. The research priorities: investment should focus on fusion energy, continued research with realistic expectations and multiple approaches, plasma chemistry, developing efficient plasma-assisted processes for green chemistry, especially ammonia synthesis and CO2 conversion, plasma agriculture, scaling up proven benefits of plasma-activated water and seed treatment, plasma waste treatment, advancing solar-powered plasma gasification for sustainable waste management, manufacturing applications, improving efficiency and sustainability of plasma processes in semiconductor and materials production. Plasma will not power everything, but it will power some things that nothing else can. The path forward is not replacing conventional energy systems with plasma-based ones, but rather intelligently integrating plasma technologies where they provide genuine advantages, primarily in specialized manufacturing, chemical synthesis, and potentially fusion energy, while powering these plasma applications with abundant, cheap solar electricity. The sun produces its energy through plasma fusion. We harness the sun's energy primarily through non-plasma technologies, photovoltaics, solar thermal. We may someday recreate the sun's fusion in terrestrial reactors, and we increasingly use solar-generated electricity to power plasma processes that enable modern technology. This multi-layered relationship between solar energy and plasma, direct, indirect, and circular, represents the real future of solar plasma integration. It's less dramatic than plasma power transmission or plasma energy storage, but it's grounded in physical reality, economically viable, and genuinely useful. That's the honest answer to how solar energy and plasma can work together to support civilization, not through revolutionary transformation of energy fundamentals, but through intelligent application of plasma's unique capabilities, powered by the abundant energy our star provides.